Okay, so my plan for this lecture is to cover 5.2 or some of 5.2, I should say. I want to first review what we covered last time very briefly, the essentials, and then we'll move into 5.2. So this will be a gentle introduction. Okay, so let me first remind you of what we talked about last time in 5.1. So this first part will be considered review. So in 5.1, we talked about continuous random variables. And from now on, I want to call these just so I don't have to write the word continuous random variable all over the place. I'm going to call them CRVs or CRV. Okay, so recall what that is. We have a random variable on a sample space, and it's a continuous function. And the probability that x lies between a and b is given by an integral of some f of x dx, where f of x is a continuous function defined on the real line, and f of x has the following property. It's called the probability density function, PDF. This takes the role of the probability mass function in the discrete case. And it has the following properties. The properties are, first of all, that f of x is always non-negative. And the second property that it has is that the integral from minus infinity to infinity of f of x dx is equal to 1. And we have also, so this is the PDF, and we also have the CDF, the cumulative distribution function, and that's usually denoted f of x or f of a. That's the integral from minus infinity to a of f of x dx. And because of the fundamental theorem of calculus, f prime of a is given by the integrand evaluated at a. Okay, so now we're ready to move into 5.2, which is about expectation and variance of continuous random variables. This parallels exactly what we did for discrete random variables. We talked about their expectation and variance. So let me first of all recall for you. Let's recall that for a discrete random variable, x, the expected value of it was you summed up over all x's x times the probability mass function of x. That was the definition. So we're going to work by analogy. So if x is a continuous random variable, we set the expected value of x to be the integral. So the sum gets replaced by an integral from minus infinity to infinity of x times the probability density function. So we integrate x times f of x. That is the definition. Okay, so let's compute some examples here in practice of how this works. So I'm going to need space for that. Well, I could probably work here on the screen. So let's see. Okay, so let's consider the case where we have the example that that f of x is the following probability density function. It's going to be 1 if x is between 0 and 1 and 0 otherwise. So this is definitely a probability density function because its graph is going to be look like this. And the area is given by the area of the unit square, which is 1. Okay, so what is the expected value of this random variable? Well, it's supposed to be the integral from minus infinity to infinity of x times f of x dx, but the function is supported between 0 and 1. It takes non-zero values between 0 and 1, so you're integrating from 0 to 1, and it's x, and f of x is given by the constant function with value 1 between when x is between 0 and 1. So you're going to get x squared over 2 from 0 to 1, and that gives me a value of 1/2 as the answer. So the expected value of this random variable is 1/2. Let's try another example. Suppose we have x, a continuous random variable, and let's set y equal to e to the power of x. Okay, so in other words, you take x, and then the value you get at and any value of the random variable x, you exponentiate it. Okay, where x is as in previous example, where you have a PDF. The PDF is given by the unit square. Okay, so in this case, let's compute. The problem is to compute the expected value of y. So how do we do that? Well, in order to do that, we do that in several steps, okay? This is actually not as easy to do directly. So what we're interested in, let's first of all compute the cumulative distribution function of this random variable y. So that the CDF, the cumulative distribution function, is given by the probability that y is less than or equal to x. Okay, but what does it mean for y to be less than or equal to x? That's the probability that e to the x is less than or equal to x. But that's the same thing by taking ln of the inequality, that the probability that x, capital X, is smaller than or equal to lowercase ln of x. Okay, and here what we get is that what is this probability then, right? Well, this is the probability from 0 to ln of x of the value of the PDF, which is 1 dx. So you're going to get ln of x. Now, the assumption here, by the way, is that ln of x is lying between 0 and 1, which is the same thing as saying that 1 is less than or equal to x is less than or equal to e. I've exponentiated the two inequalities. Okay, so we get that. So f sub y of x is ln of x if 0 is less than, I'm sorry, if 1 is less than or equal to x is less than or equal to e. Okay, now we can differentiate both sides. Now, when you differentiate the left side, you get the PDF of the random variable y, and that's given by 1 over x. The derivative of ln of x is 1 over x. Okay, so now the expected value of y, which is the expected value of e to the x, is given by the integral so it's going to be given by the way, yes. So if x is less than 1, the cumulative distribution function is going to have value 0. And if x is greater than e, it's going to have value 1. I should have written that down, but I won't write that down. So what is the expected value of y? It's the integral from minus infinity to infinity of x times f sub y of x. which is going to be given by the integral from 1 to e of x times 1 over x dx. And why are we going from 1 to e? Because of the condition we have here. Okay, now integrating x times 1 over x is the integral of 1 dx, so you're going to get x, and then it's evaluated from 1 to e, so you're going to get e minus 1. I'm kind of running out of space here on the slide, so it's going to be e minus 1 the answer. Okay, so the previous example suggests a more general phenomenon, which is called in the book proposition 2.1, which says this: if let x be a continuous random variable with PDF f of x, so then the conclusion is supposed to be that we can compute the expected value of the random variable g of x, where g of x is some function. So let g of x be a continuous function on the real line. And so we can, the statement is the expected value of g of x is given as follows. It's the integral from minus infinity to infinity of g of x times f of x dx. Okay, so the case where g is the identity function, you would get the expected value of x, and that would be x times f of x. But in this case, this is telling you what happens to the expected value for any function g. So the statement here, this proposition, the proof will be based on a helper lemma. And let me state the lemma. So the lemma goes like this. So suppose y is greater than or equal to 0 is a random variable. The values of y are non-negative. So suppose y is a continuous random variable, then the expected value of y, assuming y is non-negative, is the integral from 0 to infinity of the probability. So this is a function, the probability that y is strictly greater than y, dy. Okay, so we'll see why this is true. We're going to prove the lemma, and then we're going to prove the proposition using the lemma. Okay, so let's give a proof of the lemma. We want to prove this statement here. So why is this true? So let me give a proof. So let's first of all consider what this function probability that y is greater than lowercase y. By definition, this is given by an area. It's the area from y to infinity of the PDF, the probability density function for the random variable y. Okay. So then what? We can integrate both sides of this equation. So we can integrate from 0 to infinity, 0 to infinity. Okay. And if we do that, we get a double integral. We have to integrate this with respect to y now. Okay, so now in Calc 3, you learn how to switch the order of integration. So in order to do that, we have to write this as this is written as a type 2 region. We want to write it as a type 1 region. So let me recall what I mean. So what is the region, first of all? So it's the region here. It's the region such that x is between y and infinity. Oops. And y is going from 0 to infinity. So I want to rewrite that. So first of all, what is the region in question? So x is going from y to infinity. So it's this region here, I believe. Okay, so now we want to rewrite this. How can we rewrite this? We choose a test point in the region, and it's a point of the form xy, and we want to write it as a type 1. So we see that y is varying between 0 and x is varying between 0 and infinity. This is something you do in Calc 3. It's pretty standard. So the integral that we're looking at, the double integral, is the same thing as the integral from y going from 0 to x, and then x going from 0 to infinity, of f sub y of x dy dx. I've reversed the orders of integration. Now, this function here, f sub y of x, doesn't depend upon y, so you can bring it through the integral sign. The first integration does not affect it. It's like a constant from the point of view of the variable y. And then if we do the integral, so therefore let's rewrite it. This is the same thing as the integral from 0 to infinity, f sub y of x, the integral from 0 to infinity, I'm sorry, the integral from 0 to x, I should say, of dy, and then dx. So this is the same thing as the integral from 0 to infinity of f sub y of x times, if we integrate dy, we get y evaluated from 0 to x gives x. So it's x times f of y, f sub y of x dx. But that's exactly the same thing by definition as the expected value of y. So we're done with what we wanted to show. We wanted to show that this integral, and we should have integrated with respect to y here, which I'm doing, is the expected value, right? So that's what we had to show. Okay, so now let's go to the proof of the proposition. Okay, so what do we have to do? We had to compute the expected value of g of x. Now, the book and I will only do this, so I'm only going to consider the case when g of x is always taking a non-negative value. Okay, so that's the only case I'll consider. The statement is true in general. You don't need to assume that, but this is only handled in that case. So what is the expected value of g of x? What does that actually mean? Well, it's the following. We want to look at but because of the lemma, this is the same thing as the integral from 0 to infinity. It's 0 to infinity, not minus infinity to infinity, because of what we said before, the probability that g of x is bigger than y. This is just what the lemma says. Okay, so that's the lemma. Okay, so now I want to unravel what this integral actually means. Okay, what is it that we're doing? What does it mean to take the probability that g of x is bigger than y? Well, remember, a probability is an area, and so an area is given by an integration. It's the integral of f of x dx over the region where g of x is bigger than y. So this is the region where g of x is bigger than y. We integrate that, and then we integrate that with respect to y, as in the previous line of what I've already written. Okay, so far so good. But now, what does this actually mean? What does it mean that y is less than g of x? Well, g of x bigger than y, that region is saying that y is at least g of x. And g of x is non-negative, so y is varying between 0 and g of x. So we can reverse the order of integration again. It's written as a type 2, but we can actually rewrite it as a type 1 by means of this inequality. This is the same thing as saying that y is going from 0 to g of x. We're integrating f of x, of course, and then we integrate with respect to x. And x, where is x varying from? X is varying from minus infinity to infinity here. Okay, so I've just reversed the order of integration, just like in Calc 3. So now, again, for the same reasoning, this f of x can be brought through, okay? And the integral of dy from 0 to g of x gives you a g of x. So this is going to be, in the end, it's the same thing as the integral from minus infinity to infinity of f of x times g of x, but I'm going to write it in reverse order, g of x times f of x dx. And that is exactly what we wanted to show. So we are, and by the way, yeah, so we're done. That's it. No, by the way, we're done. So we're done for today. And that's all.